Well, welcome everybody. I am very excited for you all to be joining me today live from the California Academy of Sciences. Now, this is going to be a little bit different than our normal live streams, as normally we simulcast from the planetarium, but today I will be simulcasting from a little conference room here at the California Academy of Sciences. I'm very excited for you all to be joining me here for this 100% live show. Today, we are going to be taking a tour of the universe. We'll start relatively close to home and then make our way all the way out to the outer parts of our visible universe. And we will come back home because I promise I will not leave you out in space. Now, we will be using a program called OpenSpace. It's an open source planetarium software that helps us travel to the edge of the visible universe and back again. Now, normally we would give our house rules, but since we are not in the planetarium, we can just go ahead and start our show. Now, we are starting relatively close to home today, just a few hundred miles above the International Space Station. And the International Space Station is as far as humans do travel nowadays. You can fit about 6 astronauts on it at any one time, and it is the largest thing we have built in space. But we are going to go much farther away from our planet today. We are going to see how far our human influence has gone. We will see how far humans have physically traveled, how far our spacecrafts have gone, and how far our human communications have gone as well. But for now, the ISS is as far as humans do travel nowadays, though there are plans in the works for change that. We want to send people back to Mars in a couple of decades, maybe even the moon in just a couple of years. But in the meantime, our astronauts are traveling very quickly around our planet Earth, and it only takes them 90 minutes to orbit us just once. In fact, you can actually see the ISS pass overhead at night. Just look online and see when it will pass over your area. When you look for it, you're going to be looking for something that looks pretty bright, like a star, but it's moving very quickly across the sky. But while we're way out here, let's go ahead and bring some of the paths of the other things in our solar system. Let's go ahead and look at our closest natural neighbor, the moon. Now, the moon is our closest natural neighbor, and astronauts actually visited the moon for it took them about 4 days to get to the moon. Now, even though the moon is our closest natural neighbor, it doesn't mean that it's close in human terms. The moon is 250,000 miles away from our planet. And as we get farther and farther out today, we are going to be going distances of millions, billions, and sometimes even trillions of miles. And when we get to these big distances, it doesn't make sense for us to use miles or kilometers as a measurement of distance anymore. So from here on out, we are going to be using a different yardstick, so to speak, the speed of light, the fastest thing that we know of. Now, if we were actually traveling the speed of light, which is about 200,000 miles per second, it would take us 1.5 seconds to get to the moon. So we say that the moon is 1.5 light seconds away from us. But let's go ahead and zoom on in just a little bit closer. See those beautiful craters? Now, the moon gives an illusion that it's been hit by a lot of asteroids, maybe comets, or even meteors more often than us. You can see some really great features over here to the left, and some really spectacular ones up here in the upper right. Now, remember, Earth is actually a much bigger target, so we get our fair share of impacts. But the moon has no atmosphere. So there means there's no weathering or erosion. Also, the moon doesn't have any plate tectonics. So anything that is hit and landed on the moon, it never gets erased. So we see craters that are millions of years old. But let's continue our journey. As I said, this is our tour of the universe. And let's go ahead and bring up the paths of the other planets in our solar system. Now, as we zoom on out, we can also see the closest star to us, the sun. Now, the sun is about 8 light minutes away from us if we were traveling the speed of light. We can also see the paths of some of the other rocky planets in our solar system. Starting from the center, we have Mercury, Venus, Earth, and Mars. If we zoom on out just a little bit more, we can see the paths of Jupiter and Saturn, the gas giants. And even further out, we have the icy giants, Uranus and Neptune. Now, when we get this far out, I like to pause for a second and look at a sizable gap between Mars all the way here, and Jupiter. Now, this isn't empty space. There's actually quite a lot there. It's what we call our asteroid belt. And inside our asteroid belt is a little less known object I like to highlight. I'm going to go ahead and bring up its path, which might be a little bit hard to see, but it goes right through our asteroid belt. Any guesses on what this object might be? Go ahead and share an answer if you have an idea. So, this object is what we call Ceres. Now, it's okay if you haven't heard of Ceres before, many people haven't. Ceres is what we call a dwarf planet. And I bet you all have maybe heard of another dwarf planet in our solar system, Pluto. Now, the reason why I like to highlight Ceres is because Ceres and Pluto actually have very similar stories to each other. We first found Ceres about 300 years ago, and we thought it was the only thing orbiting in between Mars and Jupiter. So we called it a planet. But soon after, a, a lot of astronomers started finding some other rocky objects, much smaller, that they started calling asteroids. So they changed Ceres from a planet to an asteroid. Similarly, this is what happened with Pluto. If we bring up Pluto's path, we can see it in the outer parts of our solar system. When we first found Pluto, we thought it was the only thing orbiting out here in the outer parts of our solar system. But in the 1990s or late 1990s and early 2000s, astronomers were able to find other objects. Mostly small icy objects, but some of them were quite large. In fact, one was very similar size to Pluto called Aries. So instead of adding on another dozen or so planets for all of us to memorize, a group of astronomers got together and said, maybe we should come up with a better category for these small objects. So they settled on a criteria for what a planet actually is. One, it needs to orbit a star. Well, both Ceres and Pluto both orbit the sun, a star, so check. Two, it needs to be large enough, massive enough to have its own self gravity strong enough to pull it into a round or spherical shape. Well, both Pluto and Ceres are spherical, so check. And three, it needs to have cleared its path, meaning it needs to not have a lot of objects in the same area. Well, as we can see, Ceres goes right through the asteroid belt, and we have Pluto. Now, it looks like there's nothing out here, and that's because I haven't actually brought those objects up. This is what we call the Kuiper belt, and Ceres goes right through it. A lot of these objects, as I said, are small icy objects, but there are some quite large ones as well. So if we zoom on out just a little bit more, we can get a better view of that Kuiper belt. So because we needed a new definition of these objects like Pluto and Ceres, we created a new definition or category called dwarf planets. Now, I know a lot of people were a little upset when this happened, but I like to think of it this way. Yes, Pluto got a demotion, but Ceres got a promotion. And there's a whole new category of objects that we have in our solar system called dwarf planets. Okay, so I'm going to go ahead and turn off some of these objects just because they tend to slow down my planetarium software a little bit. But let's recap on how far we have gone so far. Remember, it takes about 1.5 seconds to get to the moon at the speed of light, so it's about 1.5 light seconds away from us. The sun is about 8.5 light minutes away from us. And now, if we were actually to go from one side of Pluto's orbit all the way to the other, it would take us 10 hours traveling the speed of light. So it's about 10 light hours across. Now, even way out here, we can actually check in on our human influence. We've seen so far how far humans have gone. What about our spacecrafts? So, our spacecrafts, we can see some of them coming up right now in orange, have gone quite far beyond our solar system. We are looking at the paths of Voyager 1, Voyager 2, and Pioneer 10 and 11 that were sent out in the 1970s. And most recently, the New Horizons mission that went out to Pluto in 2015. Now, these are the fastest and farthest our spacecrafts have gone, but none of them have actually traveled as far as light can in one day. So, we're going to go ahead and keep on zooming out to the outer parts of our solar system, and we're going to leave it behind and fly past some of the other stars in our own galaxy. Now, the closest stars to us, well, beyond the sun, is about 4 light years away from us. So it would take us 4 years to get there, traveling the speed of light. And even way out here, we can check in one more time on our human influence. We can see how far our radio signature has gone out into space. So we are now looking at what we call the radiosphere. The earliest radio signatures that were strong enough to escape our planet were sent out in the 1930s. So this is about 90 light years away from us in all directions. Also, we can see how many planets we have found outside of our solar system. Each ring is around a star that has at least one planet orbiting around it that we have discovered, what we call an exoplanet. And if you look inside that radiosphere, should be able to see that there are some of those exoplanets. So who knows? Maybe there's somebody listening to Nat King Cole. That would be pretty neat. But let's keep on going. We still have a lot of space to travel because we are still flying past the stars in our own galaxy. We haven't even gone outside the Milky Way yet. And as we zoom on out, I want to encourage you to keep an eye on that radiosphere. See how long it takes for you to either lose it or you can still see it. Now, we live in what we call a spiral galaxy. And we can start to see the large scale structure of the Milky Way. Now, our spiral galaxy is pretty flat and thin, It has these beautiful spiral arms made of gas and dust and stars. And we are about two-thirds of the way out from the center of our galaxy. Now, if we could see past all those stars at the very center of our galaxy, you would see, well, basically nothing because there's a supermassive black hole at the center of our galaxy and can't see anything there. Also, that supermassive black hole is about 4 million times the mass of our sun. All right, can you still see that radiosphere? Go ahead and point towards it. You're all correct because I have no idea where you're pointing. Okay, right here. That's our little area of the Milky Way. So now we're at distances of thousands of light years. From one side of our galaxy all the way to the other is about 100,000 light years across. So, if we could actually take a round trip from one side of our galaxy to the other, it would take us 200,000 years. And our galaxy has roughly about 4 billion stars in it. But we're just one galaxy out here in the universe. Every dot we see now is not a star, but another galaxy with its own billions and sometimes even trillions of stars. And the colors of these galaxies may make it seem like we accidentally spilled some cosmic skittles in the universe, but these aren't the actual colors of the galaxies. They show us the different surveys that mapped them. Now, we live in what we call the local group, which contains about 30 galaxies, large and small, including the closest large spiral galaxy, the Andromeda Galaxy. It's only about 2 million light years away from us, just next door, and heading right to us. We are going to get to know it pretty intimately in about 5 billion years. Now, as our picture expands, we discover that galaxies are not distributed evenly through space, but instead they're clumped together with great regions and voids, with very few galaxies in between. Now, as we start to see the large scale structure of our universe, some funny things start to occur. One is that it may look like a bow tie or an hourglass. Now, our universe is not shaped like a bow tie or a butterfly. That's actually, again, because we are creating the map. Remember, I told you that our galaxy is made of gas and dust and stars? Well, that gas and dust actually blocks our view. So we can't see beyond our own galaxy. So these big areas where there's not a lot of galaxies mapped, that's just because we haven't seen that. And because we haven't seen it, we're not going to show you. All of this that we have been looking at so far is based off of real scientific data, based off of what we've seen through telescopes or through different surveys. Now, you also might notice that it looks like we are the center of the universe. Well, this is not the case. Unfortunately, we are not the center of the universe. As far as we know, there is no center of the universe. Again, it's because we are creating the map. If we were to go to any other location in our universe, say over here in the upper right, or down here in the bottom center, and we were making the map, it would look like we were the center of the universe. Again, it's us looking out that allows us to see our universe, and us creating the map makes it look like we are. Okay, still have a little bit to go. Haven't reached the edge yet. And as we zoom on out, you'll start to see some of the earliest objects in our universe, what we call quasars. These are bright cores of the first galaxies. And I do mean earliest because any time that we are looking out into space, we're kind of time traveling in a way. Because the light of these objects has to travel so far that by the time it travels all that distance and gets into our telescopes, well, we're seeing the light of those objects as they were in the past, not how they look today. So, for example, when we looked at the closest stars to us, those 4 light years away from us, that's how they looked 4 years ago, not how they looked today. So now we are seeing the universe as it was billions of years ago. And because of that, that means there's only so far we can go. There's an edge to everything that we can see. And that edge is now all around us. It's called the cosmic microwave background, or CMB. Now, if we had a radio telescope and we could see in the microwave range of light, then you would see this everywhere you looked. In fact, the first radio astronomers were very confused when they put their telescopes and turned them up to the sky. They were like, what is going on? Why are we seeing interference everywhere we look? But soon they discovered it was actually something out in space they were seeing. This is a few 100,000 years after the Big Bang would have happened. So you can think of it as the baby picture of our universe, the first light that we can see. But since this is the edge of everything that we can see, means we can't go any further. So, to end our journey, we are going to head back home. Now, if we were actually that far out in space and we were actually flying the speed of light, it would take us 13.7 billion years to get home. But thankfully, with the power of our planetarium software, it will take us only a couple of minutes. And as we zoom on back home, I want you to think about one more thing. All that this we have looked at today, all these stars and galaxies and the cosmic microwave background, that's not everything in our universe. There's dark energy, this mysterious force that's causing space itself to accelerate as it expands. And there's dark matter, this mysterious substance that doesn't seem to interact with light at all, but we see evidence of it in between and the edge of galaxies, especially. And we call all these things dark energy and dark matter is because, well, we're not quite sure what they are. But we do know that they make up 96% of our universe. So everything that we've seen so far is only 4% of everything that is out there. And this may make us feel a little small, like we're one tiny dot in this homogeneous universe. But I like to think of it this way. Yes, we're one tiny dot, but look at all that we have found, almost entirely by looking through telescopes. So there's a whole lot more for us to discover and a whole lot more for us to learn. And that's what makes it a wonderful time in human history. We're not just able to learn about these things, but show them like this to map the cosmos in 3 dimensions. And we're starting to unravel the true nature of our universe. But we're only starting to unravel it. The rest? Well, that's up to the next generation of scientists back here on planet Earth. All right. Well, we are heading back to that third planet from the sun, the only place in all of this that we have found life. And that's pretty incredible to think about. So I want to say welcome home, everybody. And I hope you enjoyed our tour of the universe.